Okay, so let's talk about section 5.3 enthalpy. So I think there is a little bit of confusion when starting this. We use this term enthalpy, not entropy. Entropy we're going to get to at some point. Anytime you hear the word enthalpy, I just want you to think energy. That is ultimately what it is. We're always talking about the energy, and we're going to talk about the pressure and volume component that makes this enthalpy, but ultimately anytime you hear the term enthalpy, we're just talking about the energy of a reaction, the energy of a system, the energy of a molecule, the energy of a bond. All of that stuff just comes back to just being energy in the end. So we look at internal energy. Okay, so internal energy is just kind of the sum of all the kinetic energies and the potential energies of a system. And so when I say a kinetic energy, okay, what I'm really talking about is any kind of motion. So we're going to have a couple of different types of motion. So translational motion, or rotational, or vibrational. All of these are a molecule moving around. So translational is it moving from left to right. A rotational is it spinning around. Okay, so if it's like spinning on its axis, that would be rotational. Vibration is just a bond lengthening or shortening. So the length of a bond improving, so getting larger or getting smaller. All of that is just kinetic energy. So kinetic energy is the plus the potential energy. All of that together gives us the total internal energy of the system. Some books use U, some books use E. It kind of depends on the book that you have. The one that we really want to focus on is internal energy comes down to Q and W. Those are the two things that make up overall energy of a system, overall energy of pretty much everything, energy of the universe. Q, we are talking about heat. Okay, this is typically the result of a reaction, a temperature change. Heat is produced. And we're also going to have the W term, which is work. Work is the capacity to move something. So I've got a cup here. If I set it down, me picking it up and moving it, that distance that it covers plus the mass that I'm moving, that's the work term. Heat is the transfer of heat or energy, thermal energy. Work is the movement of matter. Okay, so there are a couple of sign conventions that we have to kind of take a look at in terms of this. So a positive Q means the system gains heat, and a negative Q simply means that it loses heat. The question is where. And so whenever I say a system gains or system loses, we're talking about it going from the system to the surroundings or from the surroundings to the system. So it's always this transfer between the two. Okay. Versus work being done on the system versus work being done by the system. So does the system do work on the surroundings, or is the surroundings doing work on the system? And typically what we're looking at there is a movement of mass. And that's why we don't typically talk about work much in chemistry terms, because we generally don't really see many pressure changes when we're dealing with like normal bench chemistry in like a general chemistry 1 class or 2. So generally, work is the movement of matter, and we don't really move a whole lot of matter in terms of physically moving it, but we do see a lot of heat changes. Okay, so here is a typical kind of breakdown of the whole thing. And by the way, the overall system change that we're looking at is a positive Q versus a negative Q. A positive Q that means that there's a gain of energy by the system and it's pulled in from the surroundings. And a negative means there is a loss of energy by the system and it has to go into the surroundings. So we'll talk about those implications. In a moment. So here we have the surroundings and the system. Now, the surroundings and the system is typically talking about the reaction. So if I were to take some kind of, some kind of chemical reaction, the chemicals that are mixing, the reaction that's going on, that's the system. The molecules that are reacting together, that's all the system. The surroundings would be the solvent that it is in. So if we're doing this in water, for example, the surroundings are just the surrounding water molecules. Okay, so the system and the surroundings are kind of mixed together in this way, and there's not like a very firm boundary. In some other situations, it's not, like calorimetry, for example, it's very clear where the system and the surroundings are. But when you have a reaction running, they're kind of interspersed. And so we kind of are looking at the water versus we're looking at the chemicals of the reaction. And so in any event, let's take a look at these different signs as they pertain to system changes in heat or changes in work. So the Q into the system. So if the system is gaining heat, okay, if it's gaining heat, the system is gaining heat from the surroundings, that is a positive Q. So the heat is flowing from the surroundings into the system. What this might actually look like is it's getting colder here and it's getting warmer in the system. Okay, so the system is requiring some amount of energy to be put into it, and we typically would see this in the form of a basically it gets colder. The water in this case would get colder, versus if we had a negative Q where the system is releasing a bunch of heat energy, it's getting hotter outside of the system, or the water is starting to warm up. Okay. And the other version in looking at work, and work is much harder to look at. So if I have a positive work term, we would typically look at this like if there was a piston, or if there was a reaction being run in a vessel with some kind of weight on top of it. So this is kind of my thing that can move, and this has some kind of mass, and some reaction happens. And if the system is pushing down on that mass and moving it, reducing the volume, that would be a positive W. But if the system is creating force, this would be a negative W versus a positive W. Depends on which way that piston, or really that weight, is moving. So again, we don't really deal much with mass. But overall, those two things put together give us the delta, the change in total internal energy of the system. Again, I want to point out the fact that most of the time we're just looking at heat. We don't really worry about the work portion of it too much. So that brings us to the first law of thermodynamics. Energy can neither be created nor destroyed. It is just converted from one form to another. We're going to see a lot of this. We're going to see a lot of it being converted from one form to another, going from like a chemical bond. There's energy in a chemical bond, to heat, right? It's going to release heat by changing or changing somehow. All right. So calculate the change in internal energy of a system that releases. And so the important part here is we need to look at the words. We're not always going to be given a sign. We have to decide which sign it is. So if, in this case, I've got my system and I have my surroundings. Okay, and calculate the change in internal energy. So the total change in internal energy, we'll use U, is equal to Q plus W, those two terms together. And so we have to decide, okay, calculate the change in internal energy of a system that releases 1.34 times 10 to the fourth kilojoules. So we're seeing a release. That is a negative Q. Energy is being released into the surroundings. So negative 1.34 times 10 to the fourth kilojoules of energy. There's my Q term. And does 2.98 times 10, and I can actually just put the number here, I've got to decide the sign in a moment, times 10 to the fourth kilojoules of work on the surroundings. So again, it's going from systems to surroundings. So it's doing the work on the surroundings. So it's pushing against the surroundings, expanding. And so we see that as a negative Q as well. Overall, I don't really care so much about the number. I just care that this is a negative energy term here, overall internal energy of the system. Okay. Okay, so the same kind of question for this, for the second example, calculate the internal energy, decide whether we're dealing with positive or negative. And in this case, you can probably determine what the overall is, but just tell me if it's positive or negative. That's going to be the important part here. All right, so before we continue and we talk about changes in enthalpy and changes in energy, we're going to get to that in a moment, and a bunch of different ways that we're going to look at enthalpy. We need to talk about a state function, the idea of a state function. So a state function is a property whose value only depends on the state and not state of the system and not the path that it took, only present on the state. So really what this says is a state function is only interested in final and initial states. I don't care about the path. I don't care if it took me 12 reactions to go from reactant to product, or 10 different steps. I don't care about any of that. All I care about is where did I start and where did I end? The overall change is what's important to me. All of the other factors, adding energy, losing energy, will not matter. And so the best example I can give is if we look at these two paths here. I've got a red and a blue up this mountain. Okay, so there's two things that I can measure. One, let's decide which one is the state function. I can measure the distance traveled. So distance traveled. We've got two sets of people going on a hike. And what do we got? So let's say that the people in the blue traveled 5.2 kilometers. And the people in the red, they took a much more meandering route, probably a much less steep route overall, and they went 9.3 kilometers. Okay, that's it. So this is not a state function. This is not a state function because the distance is different. The number is different between the two. They had the same initial starting point and they had the same final ending point, but the numbers are different. So the fact that the numbers are different states that, hey, distance is not a state function. The path does matter, okay? Versus looking at something like altitude. If we take a look at altitude, okay, so the people both started here at some initial altitude and they ended up here. Okay, so if we say that this was, I don't know, 1,000-foot climb or 1,000-meter climb, I have no idea if that's huge. I'm sure it is. If that was 1,000 meters, and let's say that that's 2,000 meters. So the final state for both of them was 2,000 meters, and the initial point was 1,000 meters for the total delta of 1,000-meter climb. And therefore, the altitude both of them climbed is, so the blue team went 1,000 meters up, and the red team went 1,000 meters up. Overall, what this means is this is a state function. The path is unimportant. The fact that they both covered the same altitude says that altitude is in fact a state function. I don't care about the path you took. All I care about is the final and initial locations. So that's the state function. That's going to be important because we're going to have a bunch of reactions, and those reactions are going to lead to ultimately, I only care about the final and the initial state, and that's what we're going to look at. So how much energy is required for, and so we've got a handful of stuff happening here. So we can think about these. We're going to use these we're going to look up a bunch of physical constants here. Okay. So how much energy is required to heat 125 gram sample of ice at -30 of water to 75 degrees Celsius? Use the appendix to get these physical constants. So we kind of have just jumped from one state. So let's figure out if path matters and kind of see where we go from here. Let's see, enthalpy. I think this is kind of in the wrong order, but that's fine. Oh yeah. We're going to come back to this one. Yeah, we're going to come back to this one. This one's in the wrong spot for sure. All right. So let's talk about the term enthalpy. Again, whenever I say the term enthalpy, what I really mean is energy involved here, okay? The enthalpy is the sum of a system's internal energy and the mathematical product of its pressure and volume. So essentially, it's the overall change in its energy. Enthalpy can't be measured directly. We can only look at changes in enthalpy and compare them to one another. So we're going to rewrite, we're going to have our enthalpy. So H is going to represent, H represents our enthalpy. U, again, is their internal energy. Okay, and pressure is pressure and delta V. So enthalpy change at constant pressure. We're going to find out that pressure and work volume is very different than pressure and volume work is kind of the thing that we're going to end up ignoring. But here we have a reaction. I've got some zinc here and we're going to dump it into with the HCl. I've got a closed system here. You'll notice that this piston is pushing down. If I flip this around, I'm going to allow that zinc to fall in. It's going to start to react. It's going to produce a bunch of bubbles. The bubbles are going to push against this and they're going to expand the space. This would be the work term. The pressure and volume component is the work term. So when we're at constant pressure, this is ultimately what we have. We're going to skip kind of ahead to what happens if we substitute the enthalpy equation. So changing things around. So here we have the enthalpy equation with internal energy and that new negative work term. Okay, so this enthalpy is, remember, internal energy was Q plus W, and we determined that that increase in volume, that pressure at a constant pressure, that increase in volume is a negative work term. Well, delta H is equal to Q positive Q, or Q plus W minus W. And we'll notice that these two things are going to cancel each other out. And we're going to be left with just Q. So enthalpy is really going to be just at constant pressure. It is going to be essentially delta H is equal to Q. So enthalpy energy is equivalent to the heat transfer between the system and the surroundings. Okay, so it's important to recognize that we do kind of ignore work, but it doesn't just kind of disappear on its own. It actually goes somewhere for a reason. So let's talk about chemistry now. Let's actually talk about these things applied to chemistry. So combustion, delta H energy, again, enthalpy, we're looking at delta H. When we see delta H, really what we see is delta E, the delta H of combustion. So if we burn something like methane, okay, methane gas combined together with oxygen gas, and we're going to balance this out as we go, is going to produce CO2 gas plus 2 water molecules in a gaseous form. For all of that, there is a delta H involved. That delta H, the cost of combusting that, okay, is 890 kilojoules of energy. So 890 kilojoules per mole of really methane. So every time we run this reaction, see, there's that 890 kilojoules per mole every single time we run that reaction. So we can have delta H's of combustion reactions, and we've got a bunch of different combustion reactions listed here. Okay. And we're not just limited to that type of combustion reaction. I can take 2 hydrogens combined with some oxygen. I can combust that and make 2 water molecules. And there is a delta H associated with that. We can see the delta H of hydrogen is 286 kilojoules per mole. So every single time I run this reaction, I get 286. 286 kilojoules of energy, but not quite. There is a little bit of a problem here. What we might notice is this is per mole of whatever I'm reacting, and I have 2 moles here. Okay, so in the table, I've got 286 kilojoules for the fuel of hydrogen. What we really have to do is, this equation is kind of wrong. We always have to reduce it so we only have 1 mole of that starting material. So what I'm going to do is I'm just going to multiply this reaction by a half. So I'm just going to back up and I'm going to change just a couple of things. So this number, although that's what we got from the table, does not apply because it's per mole. I'm going to get rid of the per mole. I have 286 kilojoules per mole in this case of hydrogen, right? 2 per mole of hydrogen is what we have. So if I have 2 moles of hydrogen, right? So I've got 2 moles of hydrogen. What is the energy being released by this reaction? Well, if it's 286 per 1 mole, it is going to be twice that. So you end up with 570 kilojoules. And I'm not going to put per mole this time because we don't have, it's for just for this reaction. So this reaction releases 570 kilojoules of energy. That is the delta H of this. We might type delta H of reaction is 570 kilojoules. Okay. The real reference for this is having 1 hydrogen, which would give me half an oxygen and 1 water, producing 1 water molecule. And that delta H is going to be equal to 286 kilojoules. And now I can put per mole because we do have just the 1 starting material. Okay, so when hydrogen combusts, that reaction runs once, it's 286. What if I wanted to burn 10? Then you just multiply the value by 10. So what we're finding out from this is enthalpy values of reactions are multiplicative. If I multiply a reaction by 2, I multiply the standard enthalpy by 2. By the way, what happens if I reverse it? So if I were to switch the direction of this reaction, so H2O is going to produce hydrogen and oxygen. What is the delta H of this reaction? Well, if it's 286 kilojoules per mole, and I reverse the direction, I'm going to switch that to negative. Okay, so you just switch the direction. In fact, the numbers are wrong here in terms of sign because these should be negative, but in any event. But if we flip it around, enthalpy values are multiplicative. And also, if we reverse the direction of the reaction, we flip the sign. So reversing a reaction equals flipping of the sign. Okay, good. So we have a bunch of reactions. We are not just limited to something like combustion or a chemical reaction. We have a bunch of different terms that we're going to use. They're all delta H's though. They're all reactions that we can write out. So if I have something like, what is the delta H of fusion? We're going to use water because that's the best example. Remember, fusion is one of these weird words that we use in chemistry. It's going from solid to liquid. It's our way of saying melting, although it sounds like fuse, but it's from the Latin. So that means that the reaction written would be solid water converting to staying water and going to liquid. This is the delta H. This is a delta H of fusion, okay? And we have a delta H associated with that. Delta H of fusion of water is equivalent to 6.02 kilojoules per mole. So every mole of water, that's the delta H of fusion that we're dealing with. Delta H of vaporization. Delta H of vaporization, vaporization's going from liquid to gas. So we'll start in the gaseous, or start in the liquid state. We'll convert that water into the gaseous state. My delta H of vaporization that is going to be equal to 40.7 kilojoules. I got these numbers from the table. You can find them pretty much anywhere. Just look up an enthalpy table and generally you'll find them. There we go. And then we have sublimation. Sublimation is going to be going directly from solid to gas. So we'll start with a solid. We'll convert that water to a gas. Delta H of sublimation. What is the total of that? Well, enthalpy is a state function, okay? Because enthalpy is a state function, going from solid to liquid, then going from liquid to gas, that's the energy that it costs to do those two. So it turns out the enthalpy of sublimation is actually 46.72. Yeah, 46.7 kilojoules per mole. It's the combination of those two things. So it's just simply adding those two things together. Enthalpy is a state function. That's what we pull out of this. That's the difference between those two. Okay. So by the way, what is the delta H? Just as a quick aside, what is the delta H of freezing of water? So the delta H of freezing is what? Well, if going from solid to liquid is 6 kilojoules of energy, negative 6.02 kilojoules per mole to freeze something. Because again, we're flipping the sign whenever we're dealing with moving in the other direction. Okay, so we've got delta H of fusion, vaporization, freezing, sublimation, condensation. You have delta H's for every physical process and every chemical process. And we just have special tags for a lot of these because we use them relatively regularly. Delta H of solution. Well, delta H of solution is just me taking something like sodium chloride in the solid state, dropping it into an aqueous, into a water, making HCl. Sodium chloride and aqueous. So dissolving water, dissociation of those ions. We end up with this is my delta H of solution. In order to do that, you don't get much energy from this or energy change from this, 4 kilojoules per mole. So it's really tiny, but again, by changing its state, it still has an energy associated with it. All of these things do. In the end, what we're going to come to is a positive delta H is endothermic. We often put this into cooling down. Really what this is energy or heat going from the system to the surroundings. So I'm sorry, the other way around. The heat is coming from, I'll just say it instead of writing it, the heat is coming from the surroundings into the system. Because the surroundings are starting to warm up the system or put heat into the system, the surroundings are losing energy and it's cooling down. A negative delta H is exothermic. So in this case, the heat is going from the system into the surroundings. So the surroundings are gaining heat and therefore it is warming up the water or the surroundings typically. Okay, so that's it. So that's the idea for system and surroundings. My point being is sign is going to matter. We have delta H's for essentially all of these different things. And all of these different changes, and we need to take those things into account. Okay, so with all of that said, now I remember why this was here. How much energy is required to heat 125 gram sample of ice from negative 30 to 75 degrees Celsius? So we have looked at calorimetry and we've looked at specific heats. And so what we have is I have the mass of 125 grams of ice or of water. The delta T, this is me doing it wrong, by the way. The total temperature change looks like it's 105 degrees Celsius. And we know that the specific heat of water is what, 4 Yeah, the specific heat of water is, well, we actually have two specific heats of water because we have water and ice. So we have two specific heats present here. And so the specific heat of water, so we'll call it C, specific heat of ice is 2.09 joules per gram times degree C, and the specific heat of water is 4.184 joules per gram times degree C. And so what we have to take into account is, hey, how much heat, Q, for going from that mass of ice over a specific temperature change. So going from ice to 0 degrees Celsius, right? So we're going to go from ice to 0 degrees Celsius. That Q is going to be equal to, well, the specific heat of ice is 2.09 joules per gram times degree C times the mass, which is 125 degrees Celsius, times the temperature change. I'm going from final minus initial. The final temperature is 0 degrees Celsius. The initial, by the way, I should do this in Kelvin, but I know that it's going to be an absolute value, so I'm not worried about it. Negative 30 degrees C. So overall, that's a 30-degree change. And so now I can just simply do the math. You end up with 8 kilojoules of energy. So my question to you, I suppose, is how about going from 0 degrees C to 75 degrees C? How much energy does that cost you? Okay, so do the math, pause this and do the math. You should end up with 39 kilojoules of energy. Okay, so together, that should cost us 47 kilojoules of energy to go through that change, or so we think at this point. All right. So up to this point, we've looked at the specific heat and changes, but we kind of have to look at this in a little bit of a different way. So first of all, going from a solid, a liquid, and a gas, their heat term is controlled by, the heat term is always controlled by mass times specific heat times the delta T. We also have to keep in mind that there is a delta H. There is a, when I'm going through this, what we call an isotherm, okay? When we're going through this temperature change or going through a phase change, there is also energy associated with going from a solid to a liquid. We don't go from the example that we had, we don't go from directly from a solid immediately to 0 degrees, and then from 0 degrees, it's automatically a liquid, right? What ends up happening if you boil water on your pot, on the stovetop, you could let there and let it boil and let it boil and let it boil, and the temperature is never going to change. It's always going to be around 100 degrees Celsius. It's always going to boil at that same temperature. Okay. It would start to overheat if you let all of the water boil away, then you would burn whatever you have in there. But the idea being is, as long as water is present, as long as a phase change is happening, you're not going to increase the temperature anymore. And so when we go through a phase change, we also have to take that into account. So when we're looking at changes and they pass a phase barrier, so in the example that we just did, we determined going from negative 30, I think it was negative 30 to 0 degrees Celsius. And then we determined going from 0 degrees Celsius to 75. The thing that we were missing was, hey, how much energy did it cost us from that delta H of fusion? So let's take a look, and this will show you the example if you ended up getting it right or if you tried it. So going from 30 to 75, going from ice to water, I see this differently, or we should see this differently as chemists. Okay, so going from ice at 75 or negative 30. So what we start with is step one. It's negative 30 degrees Celsius as a solid. And so what I'm going to do is I'm going to increase the temperature. I'm going to figure out how much it costs to go to 0 degrees Celsius, but we're still in the solid form. So we're essentially just getting to this point here in our reaction, okay? And that is controlled by Q is equal to specific heat times mass times delta T. And this is what we just did. And so I'm just going to repeat that. 2.09 kilojoules per mole. And the moles are going to be important. Kilojoules per gram. We're not dealing with moles. Sorry. You can, but this is going to be gram times degree C. In fact, let me rewrite this in a different way because that's a messy thing there. Joules, I'm going to put this properly. Moles times degree C. Oh, I did it again. Not moles, grams. All right. Times the mass of 125 grams times the delta T. And so my delta T is going from 0 to 30. I'm not going to do the final minus initial. It's 30 degrees Celsius is the gap. So in terms of units, grams cancels, degree C cancels, and the remaining unit is going to be joules. And if you do that math, you're going to come out to about 8 joules of energy. So to go from negative 30 to 0, 8 kilojoules of energy. All right. The next step is we actually have to go from 0 degrees Celsius as a solid to 0 degrees Celsius as a liquid. So we're going to convert it from solid to liquid. The problem is I don't have a delta T, so I can't use the equation that I did above. We have to use the delta H of fusion equation, or we have to use the idea of delta H of fusion. So if I look in my appendix, what I find out is, first of all, the delta H of fusion, actually, I'm going to write out the reaction. So what this is really happening is this is a phase change. Water solid to water in the liquid state, where the delta H of fusion, again, that is the melting of water, is equivalent to 6.02 kilojoules per mole. Again, I looked this up in an appendix. We can always use our units to get us there. So my Q in this case is equal to delta H times N being the number of moles present. Okay, so I'm going to have to do a quick conversion. So I'm going to do some quick math on the side here. If I'm trying to figure out the moles of water, well, I have 125 grams of water, and I want to convert this into moles. We're always going to have the amount. You should always have the amount. It's about 18 grams per 1 mole. That's the molar mass of water. That's going to give me 6.9 moles. Probably should have one more sig fig, but that's fine. 6.9 moles of water. So my delta H of fusion is 6.02 kilojoules per mole. My moles was 6.9 moles. My moles are going to cancel, and I'm going to be left with just kilojoules. And this comes out to 42 kilojoules of energy in order to do that change. So quite a bit. It cost us quite a bit to go from solid to liquid. And then finally, step 3, this is the one that I had you do above, going from 0 degrees Celsius as a liquid, converting that to 75 degrees Celsius as a liquid. So we switch from solid to liquid, and now we're going from liquid to liquid at a higher temperature. So again, we're going to use Q is equal to specific heat times mass times delta T, and we can plug in the numbers. So I look up the value of water, 4.184. Actually, this is joules. Did I convert that to? Oh, okay. I think the first one I just skipped right to kilojoules. This one is joules per mole degree C. It's fine that's what, and the mass is 125 grams, and we have 75 degrees C. Okay, so again, degree C cancels, grams. Oh, I did it again. Grams cancels. Keep doing that. And you end up with 3,900, I believe. But we're going to convert this to kilojoules because I want all of these values to be the same. And we add them all up, 89 kilojoules of energy. And that's why we need to make sure that the units are all the same. 89 kilojoules of energy in order to go through this phase change, go from -30 as ice all the way up to 75 degrees as water for 125 grams. Okay. So again, when you're going through a phase change, you have to use an enthalpy of reaction or enthalpy of that specific process. All right. So now we're going to look at enthalpies of reaction. So this is a generic one instead of looking, and this we can also use this for pretty much anything. So enthalpy is an intensive property. Okay, so it is, is an extensive property. So it does depend on the amount that you have present. So if you have 1 mole, if you have 100 grams, like all of that stuff is going to be important. So here I have a reaction, and you're always going to kind of see them written out this way. This reaction is giving you this much energy associated with it. So the energy associated with it is per this reaction here. So 890 kilojoules of energy. This is also a conversion, by the way. There's a number of ways that I can write this. In fact, I can write this that 1 mole of CH4 is equivalent to 2 moles of O2 in this reaction, which is equivalent to 1 mole of CO2, which is equivalent to 2 moles of H2O. So this is all stoichiometry. That's the stoichiometric ratio. But we can also add to this -890 kilojoules of energy. So we've now associated those molar quantities with an energy. So if I'm asking a question like this, what is the enthalpy of change associated with a combustion of 0.75 moles of methane? Well, if I start with 0.75 moles, because that's my non-conversion, that's my measured number of CH4. I want moles of CH4 to go away, so I'll put that on the bottom. And I wanted energy, so 890 kilojoules of energy on the top. 1 mole, according to this, 1 mole of CH4 is equivalent to that much energy. By the way, if I said, hey, I've got the same amount of oxygen, again, you have 2 moles of oxygen for that much energy, and you can calculate that as well. So we can do the calculation here, and we should end up with -668 kilojoules of energy is released because it's a negative. So this is an exothermic process. How about 3.25 moles? How much energy do you get released, right? What happens if you have, how about if you have 3.25 moles of O2? How much energy gets released, right? How would we calculate that? So figure those two numbers out. We'll take a look at that. All right. So enthalpy change for a reaction. So we already talked about this, but if I reverse the direction, reverse reaction, we have the opposite, okay, 890 kilojoules of energy. So we went from positive to negative because we've reversed the direction of the reaction, okay. Good. Enthalpy change for the reaction does depend on the states. The states are actually super important. So up here, my reaction is, you'll notice, gaseous, 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 liquid. Down here, I have gas, 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 gas. Everything is gas. So the water here was liquid, okay? So if we want to, it does depend on the states. And so what we have is 802 kilojoules of energy when they're all in the gaseous state. So again, above this was, I want to figure out, hey, that was liquid. So I want to actually change that back to liquid. And we can kind of screw around with these things. We can create a new reaction, okay? So what I want to do is I want to get rid of all of this. And in order to do that, I need to essentially have that cancel out. Okay, so if I'm to combine these two reactions together, and don't write this just yet, I need to make sure that on this side I have 2 gaseous waters, and then they're going to cancel. So we are allowed to do whatever we want to these reactions, as long as we kind of keep track of how we change the delta H. Okay, so for this one, what we're going to do is we are going to, oh, I think I messed this up too. Yeah, let me just fix this. It's not 88 kilojoules. It is 40.7 kilojoules, positive 40.7. So yeah, because that's important. It's really important. So what I want to do is I want to recreate, ideally what I want to get is I just want to change this right here to liquid. Okay, so I want that to be a liquid. Okay, so in order to do that, what do we have to do? Well, all of this stuff is just fine. So I can just rewrite that reaction. I can rewrite this whole reaction because I need all of this. Gaseous 2O2 as a gas yields CO2 as a gas plus 2H2O. I can't just change this to liquid. I have to justify that with my delta H. And my delta H for this reaction is negative 802. I haven't made any changes for it. So negative 802 kilojoules. I haven't made any changes yet. I'm going to take this reaction here. I'm going to reverse it, and I'm going to double it. Okay. By doubling it, it's going to allow me to switch those. So I'm going to reverse it. So I end up with H2O. I'm going to leave some room so I can get rid of it. And H2O liquid. Okay. And now I'm going to double it. Okay. So I've reversed this reaction and I've doubled it, and it's given me this new reaction. Well, by reversing it and doubling it, I will now, I can cancel anything on the left and on the right. Okay, so notice that I have two gaseous waters here and two gaseous waters there. Those things, because they're on opposite sides of the arrow, they're going to cancel out. They don't need to be there. Okay, you can write it all below, but that's what you get. So what I have left, CH4 gas plus 2O2 gas yields CO2 as a gas plus 2H2O as a liquid. So I have accomplished changing this from gas to liquid. That was the goal. Okay. So we know that the temperature, we know that the temperature or the delta H of that is 890, but the delta H of, so how has delta H changed? What's the new delta H for this? Well, delta H is going to depend on the changes that we made. So again, for this reaction, I reversed it. That means that I'm going to change the sign. This is now going to be a negative 40.7 kilojoules. By the way, I also multiplied it by 2. So this whole thing is going to be multiplied by 2. So I now have, I'm going to change that to negative, essentially negative, what is that? Negative 82. I'm just going to round it to 82 kilojoules. So negative 800 minus combined with the negative 82 gives me negative 884 kilojoules. Not perfect, but very close to my negative 890. Okay, so there's a couple of things in there, but that's ultimately what we have. It kind of depends on the data stored, but very close. So we can kind of make reactions change by combining their enthalpy. So I have a new reaction and I can determine the enthalpy of that. All right. So this brings us to the idea of Hess's law. And I think we got a handful of other pages of this. So I'm going to stop this here and I'm going to pick up Hess's law in part 2 of this.